then the debugger can use this setting for watching ports. It is not very much known. So here is a general formula how to set the debug registers. We can set 4 hardware breakpoints, yes, from debug register 0, 1, 2 or 3. Then we just load the address into debug register, and then we can use this formula to set the debug register 7. After this is finished, the hardware breakpoint is finally set.
Just a second, that's a question from Hydro. He asks, is there any trick you can use to break debugging in your debugger? Like it could be broken.
I am better reader than here.
Yeah.
Yeah.
Why don't you repeat the question?
There is a lot of tricks. You can see the samples included in debugger. You have a lot of anti-debug tweaks there. So this is the first example. We want to watch reading or writing into one quote word at address this one. So we just load this address into debug register 0, then we read the debug register 7, we mask of all for debug register 0, then we set it on what we want, and then we write this value into this is error. Then this is changed. Move debug register 7 error x. Then we set it finally. After this setting, we can resume the execution of program and we can wait until the code falls into this prepared thread. After accessing any byte at this memory range, interrupt 1 will be triggered, and this bit in debug register 6 will be set to 1. We will discuss what does it mean debug register 6 later. This is other example. This is only because I told you that we must take care of aligning. If we want to watch writing into 8 bytes at this address range, we can't set only one breakpoint of the size of quad. It doesn't work because this address isn't quad word aligned. We have to split this address into 4 parts and to set 4 breakpoints, every breakpoint aligned on its size.
Is that for optimization or?
Yeah, it is automatization of CPU. Oh.
Oh, it looks horrible.
So at
Try to
first,
fix it. Put a smaller font or something.
delete. Put one tab here.
Done.
One again. One tab.
One tab. Okay.
Yeah.
That will work.
Yeah, now it is good.
Done.
Correct this.
Sorry.
Here's error. I want to edit. Let's see it.
That's another question from Hydrock. He's asking, how do you treat self-modified code? If you can debug self-modified code.
We can broke self-modifying using this debug, these hardware breakpoints. You have some samples included with this debugger. Check these samples. You have some tricks there. So this is the sample how to set these 4 hardware breakpoints to cover this quad word memory range. We read debug register 7, we mask off everything. Then we load debug register 0, debug register 1, debug register 2 and 3 with corresponding addresses. And we set on corresponding bits in debug register 7. These bits for debug register 0, these bits for debug register 1, and these bits for debug register 2, and these bits for debug register 3, another arrow. It should be debug register 3. Yeah, and at the end, we write the value into debug register 7. No, it's correct. This is loading address. Yeah, debug register 3. It is. It should be debug register 3. And after this setting, we are allowed to resume the execution of code, and we can wait till some instruction accesses the memory at this memory range. Example 2, we want to break on the execution of the instruction at address with this value. I must to say that the instruction must start exactly at this address. The instruction mustn't start at the address 34. It must start exactly at 35. If this address lies somewhere inside the instruction, so the instruction has 2 or more bytes, then the interrupt 1 won't never occur. So we just load this address into debug register 0, then we load the value of debug register 7, we mask off all necessary bits to prepare to put what we want to put into it, and at the end we write it into debug register 7. This is the example which M. Hajduk asked how to break self-modifying. This is example 3. This is the most amazing example, but the worst formatted. This is example from yeah. So put up there. So let's try to put up here. Yeah. Yes. And then again. This is possible in kernel because there are some tricks under user mode protection level how to access ports, but under 46 bits of operating systems it is very limited. And the people usually don't know that we can use debug register to watching, reading or writing into ports. It is very useful in kernel. We can prepare this type of breakpoint for accessing the ports what we want. The kernel must enable this 1 bit in control register 4. This instruction can be executed only in ring 0. We read the control register 4. We enable the bit 3. Then we write the value back into control register 4. So, and then we prepare the debug registers. I wanted to show that we can use 4 debug registers, not every time only debug register 0. I used debug register 3 in this example. So we just read this is error. We just write the value of the port of our interest into debug register 3. Then we set these bits in debug register 7. At first we mask it all bits off, and then we turn some bits on. This means that the length is 8 bytes, and this means that the type is triggering interrupt 1 when accessing port from 20 to 27. It is 8 ports. And at the end we write this value into debug register 7. And then everything is prepared until kernel accesses one of ports in this range. After accessing these ports, the interrupt 1 is hit, triggered. This is very useful in kernel, but I suppose that is not implemented in Windows or in Linux.
That's a question. They're asking if will it be better to use a high-level debugger for high-level code, or if you think that a low-level Arsenal debugger will also be good for high-level code as well. At least that's how I understand the question. So if you read from here.
But all high-level code is going to be anyway after the compiler low-level code.
That's true, but
the problem of high-level
semantic information.
The problem of high-level language is that it adds a lot of ballast into program, and you have to think what does it mean.
Yeah, you have to know what the compiler has been doing. It's
the best way how to debug this program is to focus on some API and to put breakpoint on this API and stop the program at the API. I often do it in this way because the program is huge and the orientation is difficult. So I told you that after the interrupt 1 is hit, we have the debug register 6. Its name is debug status register, and when the interrupt 1 is hit, this debug register 6 holds the name of event which led to triggering this interrupt. We can say that the interrupt 1 is a big container holding a big mess. Perhaps 5 various conditions may lead into triggering this interrupt 1. So when the debug register 6 has set the bit 14, it means that single step occurred as a result of enabled track flag registers of bit of flags. If the bit 13 of debug register 6 is set, it means that some program tried to access, it means tried to read or write some debug register. It is the way how to observe that somebody was trying to reading or writing into debug registers. And when one of these bits is set, it means that the debug register 0, 1, 2, or 3 was hit, the address in this register. And this is one perhaps complication or improvement. When the bit 13 of debug register 7 is set, we can set this bit to enable detecting accessing of debug registers. Yeah? When this bit is set, this interrupt 1 triggers when an attempt is made to execute a move debug register instruction to any of debug register. But I showed you that the interrupt 1 handler often uses reading or writing into these debug registers. So CPU has the protection mechanism not to trigger the interrupt 1 again from inside, and this protection is based on the fact that just before the interrupt 1 is hit, the processor clears this bit to 0 if it was enabled, and it prevents to trigger interrupt 1 by accessing debug registers in interrupt 1 handler. And software debuggers can use this bit to prevent the program for interfering with the debug operations.
So you could use that to emulate debug register access and turn off, well, not turn off debugging, but make it appear to the user mode program that debugging was turned off. So you can make a shadow copy of the debug registers that looks like the program would be expecting.
Perhaps. So here is a sample of interrupt1 handler. We just load this debug register 6. At this point, the CPU cleared the bit 13th, so this accessing of debug register doesn't cause the triggering interrupt again. So we just, without worry, we can read this debug register and we test bit 13th. If this bit is set, the cause of triggering of interrupt 1 was single step. It means the setting of trap bit of flag register. When the bit 13 of the debug register 6 is set, it means that some program tried to access debug register. If the bit 3 is set, then the breakpoint 3 occurred. When the bit 2 is set, then the breakpoint 2 occurred. When the bit 1 is set, then the breakpoint 1 was triggered. And when the bit 0 is set, then the other breakpoint number 0 occurred. And if none of these bits is set, that it was the instruction ICEBP which caused the interrupt 1. There are no other possibilities, but you see that interrupt 1 is really big trash holding everything together. Instruction execution breakpoint and the general detection condition cause the interrupt 1 exception to occur before the instruction is executed, and the others are triggered just after the instruction is completed. But every rule has exceptions, and this one has 2 exceptions. For example, if we have instruction with read prefix like repeat to 0 moves, then we can breakpoint between the iteration no, nor, no at the end of the instruction. Of course, we can set 2 hardware breakpoints, one of instruction execution, and at the same instruction we make access the memory. In this case, the first occurs the execution, and this occurs at the start address of this instruction. And after this breakpoint, as the second, occurs the accessing of memory, and this occurs after the instruction completes. So the second address is reported after or at the end of instruction, on the start of the following instruction. Single step, what does it mean? This single step triggers interrupt 1 again, just like debug register. It's the same breakpoint, the same interrupt handling, single stepping. Single stepping is very easy to do. I showed you the example, which said thread flag bit, it is bit 8 of flag registers. Push flags or the word at stack pointer with 1, shift left 8, and pop flags, and this bit is set. When single stepping is enabled, the interrupt 1 exception occurs after every instruction which executes, until this bit is disabled and cleared. But the instruction which sets the thread flag bit and the following one is not single stepped. I explain it.
Just a second. low-code assembly is asking
Yeah.
if FTDD works only with 64-bit or only or
No,
or
it
32-bit.
works with 16 bits too and with 32 bits too. It's the same.
Okay.
This single stepping isn't platform dependent.
No, he asked if your debugger supports both 32 and 64-bit mode. Not the exceptions and all that, but your debugger.
No, this debugger will be only 46 bits. The making 64 bits, the making 32 bits requires to make disassembly engine for
Yeah.
32 bits at it.
And
The engine for 46 bits consumed me about half a month of the work.
Hajduk asks if your debugger could save your disassembled code, or if it's just going to be a debugger.
I completely left the old 32 bits world. I wanted to make debugger for 46 bits, which nice user mode GUI interface for beginners, especially. So this is the sample. I will explain what happens. We push flags, then we turn on this bit 8 in stack, and then we write it into flags back. At this point, as this instruction is completed, the track flag is set. But at this point, interrupt 1 doesn't trigger yet. Just after executing the following instruction. After executing this instruction, at this point, the interrupt 1 occurs for the first time. The track flag is set, and when after the return from interrupt, we will return on the second instruction here. After this instruction completes, the interrupt 1 occurs again because the track flag bit of flag register is still set to 1. So interrupt occurs second time. Now we will return from interrupt 1 here, and the CPU executes this instruction. This executing causes the triggering of interrupt 1 again. It is the third time. After returning from interrupt 1 handler, we will get here. But we prepared in stack the image of flag registers with disabled the track flag register. And after executing this instruction, the interrupt 1 occurs again. But it is the last time, because after popping flag from stack, the track flag is cleared. So we return from the interrupt 1 here. And now this instruction doesn't trigger interrupt 1 anymore. Now we will execute instruction without triggering interrupt 1. The executing of this instruction is slower than this, because several instructions executes of the interrupt 1 handler before returning to the next instruction.
And also the user versus kernel mode switching back and forth is very expensive.
And under Vista it is extremely slower to make single stepping. To let the program single step, it is
So it's
very
slower on Vista than
slowly, because the overhead of operating system. The bigger operating system, the more instructions in interrupt 1 handler.
Yeah.
So this is the skeleton of interrupt 1 handler for single stepping. Some clever man might think that the track flag is still set on. And why? Every instruction inside the interrupt 1 handler doesn't cause interrupt 1 again. It would be terrible, because we will cycle to never end. So the CPU pushes the flag register into stack with the track flag set, and after pushing into stack, the CPU clears the track flag. So no one instruction inside interrupt 1 handler causes the triggering interrupt 1 again. Yeah, we can safely execute every instruction. It is terrible. Everything is shifted. Yeah. So the first, we save register RAX, then we test. Then we test. Then we save the debug register 6 into RAX, and then we test the 13th bit of debug register 6. And if this bit is set, it is single stepping. And if this bit isn't set, that something else led to trigger an interrupt one handler. And at the end of handling, the CPU pops the correct image of flag register with the trap flag set on. So after returning from interrupt, the trap flag is set on again. So the following instruction may trigger interrupt 1 again after returning from interrupt. This return leads to returning to begin of following instruction every time. Okay? But single stepping can be a bit more complicated. We will discuss it later. It is the simplest scenario which I showed you. What does it mean, software breakpoint? I told you about hardware breakpoints. Software breakpoints is something else. Hardware breakpoint every time triggers interrupt 1, but software breakpoints triggers interrupt 3. And software breakpoints are based on interrupt 3 instruction. We have these two possibilities how to encode interrupt 3. This one has only 1 byte of size, and this one has 2 bytes. This one is very useful because we can override every instruction, even the instruction of 1 byte size. We can override this with this 1 byte. So this one is useful for debugging, and this one is not much useful because 1 byte instructions doesn't fit into it. This instruction may occur in program as a result of debugger working when the debugger put it into running program at the time when the program is stopped. The debugger put it into the program, and the debugger waits till the interrupt is triggered and this instruction is executed. And the second choice how this instruction may come into program is when the programmer put this instruction into source of the program and incompiled the instruction into the program at development stage. At the end, the programmer must remove this instruction. That's terrible. That's terrible. The steps are very complicated. How to handle software interrupts. It's more complicated than hardware breakpoint, but we can explain it perhaps in an easy way, easily. At first, we must say how to debugger sets this 1 bit. Programmer orders to debugger to put software breakpoint at some address. So the debugger reads the original byte at the address of our interest and saves the original byte and the